So in this video, we're going to talk about the domain and range of the trig functions that we learned about in the last two videos. So I keep mentioning, this word functions, right? And it's kind of important that we remember what a function is. So, just because as a reminder, a function, what is a function? A function, it kind of like defines a relationship, right? Defines a relationship between what we call a set or a collection, a set of inputs and outputs. And in particular, it's a function if every single input, where every input goes to exactly one output. Okay. And the way that I, kind of think about this, right? So typically you can create like a little bubble here that represents, say, the domain of a function. This is like our collection of input values, and maybe our collection of output values is over here. And we can kind of think of a function, as the path that takes you from one to the other. So for instance, if we have the function f of x equals x plus 3, then if we have, for instance, x equals 2 as part of our input, then that's going to map over to it's going to map over to y equals 5 over here. And if we have, x equals 0, it's going to map over to y equals 3. And there'll be like a little map that takes them over there, and so on and so forth. And the way I remember the definition part, right, specifically, I would argue that this part, right, where every input goes to exactly one output is the key thing here. Okay, to be a function, we need this to happen. And how do I remember that? I think like if we're making a cake or something, right? If we're making a cake, eggs, flour, sugar, right, water, whatever it is we need to make a cake. Okay. And let's say that in our outputs we have like a bowl, we have the oven, we have a tray, we have the floor, okay? Different places where our ingredients could end up. A good recipe is going to say, okay, take the eggs, put them in a bowl. Take the flour, put them in a bowl. Take the sugar, maybe put it on the tray, spread it out on the tray. Take the water, put some water on the floor. This, it may not be the most natural sounding recipe, but the point is that all of those ingredients have a place to go. And it doesn't matter if they end up in the same place, right? If you put multiple ingredients in the same bowl, it still makes sense, right? One input goes to one output. Now, what would be a little less clear? A little less clear would be if they told you to put the eggs in the bowl, but they also wrote put the eggs in the oven as well, because you don't know how many eggs to put in which. You don't know. Am I supposed to put in more or less? Right? It's a little bit confusing. You don't know. It's not. These are not clearly defined instructions. So that's how I think of a function and kind of how to remember it. It'd be a bad set of instructions if they said, all right, take the eggs, put them somewhere, take the flour, put it somewhere, take the water, put it somewhere. And like, why is this bad? Well, because they said you need sugar, right? They said that's part of our list of ingredients, and then they didn't tell you what to do with it. They said, yeah, this is part of our list of ingredients, and they don't tell you, where does it go? And so in that case, you could fix that by just simply eliminating this from your list, basically removing it from your domain, removing it from your list of ingredients. And now, we're better, and the only thing we have left to do is to remove the fact that eggs is going to too many places. And now we have a function, right? We have some mapping from our ingredient list, from our set of inputs to our set of outputs. And, it doesn't matter that we're not using the tray, right? Because that's just something that exists in our kitchen, right? It's more important that the list of ingredients, our domain, that everything is being used and everything goes to one output. Okay, so that's what a function is, and this idea of domain and range. And hopefully from pre-calculus 1, we remember that, domain and range, we usually use this thing called interval notation. So for instance, how about for the function f of x is equal to the square root of x, okay? So the first thing we would need to do is we need to understand what x values can we actually put into this. Can we put in 4? Absolutely, right? Can we put in 9? Yeah, sure, why not, right? Because 4 goes to 2, right? 9 goes to, right? So 4 goes to 2, 9 goes to 3. Could I put in 7? Absolutely, I could put in 7. 7 just goes to the square root of 7, which is a number, that's fine. Can I put in 0? Absolutely, 0, square root of 0, that's just 0, okay? Could I put in a negative number, right? Can I put in -1, okay? And the answer is no, right? If we're not talking about imaginary numbers, for those of you who are familiar, if we're not talking about imaginary numbers, -1 doesn't go in, and so we don't say that the square root of x isn't a function here. What we'd rather do is what we call restrict our domain, okay? So we restrict our domain to kind of preserve that the square root of x, right, that f of x equals the square root of x is a function. Okay, so we kind of make sure that we follow our own rules, okay? And just as a reminder, remember that f here, f right there is just the name of our function. Right? This is the name of our function. We could have picked anything. My personal favorite is to write, we could have called this function Bob. We could have called this function Bob of x is equal to the square root of x, right? Whatever we want to name it, that's just the preface here is just the name. And then the x indicates this is what we're putting inside of our square root here, okay? So for instance, if we had Bob of 2x plus 3, and I was putting that inside this function, this would just be equal to the square root of 2x plus 3, right? We replace our input with our new input, and it just goes right in there, okay? So that's just kind of a little refresher on what a function is, how to think of it, the rules that we have to play along for, from kind of like the typical sense from pre-calculus 1. So now we're going to move on to, talking about these trig functions. And specifically, we're just going to talk about the domain and range. So we would like to talk about the domain and the range of all of our trig functions. And actually, let me put this over here. So domain and the range. And let's put our trig functions over here. So we have sine of x, cosine of x, and tangent of x. So I guess we're using theta, right? Remember, x is just indicative of, it just represents our input variable. So you could put whatever variable you want. We're using theta to represent angles, so I will use theta. But eventually, we will just put in x in the future because x is just our classic input variable. But for now, we'll stick with theta so we don't get confused. Okay. So the question is, what are we going to put into our function? What are we going to get out of our function? Okay, so what angles, right? So it's a good idea to maybe have the unit circle here to help us remember. Okay, the question is, if we have the unit circle, okay, what angles can I put into sine of theta and get an answer out of, right? What angles am I allowed to put in here? Okay, could I put in 0 degrees, right? Remember that sine of theta is asking, what is the y value for some angle theta, on the unit circle. Okay, this is the easiest way we have to really understand what this means. So, at 0 degrees, we know the y value is 0. At 45 degrees, we know it's root 2 over 2. At 90 degrees, we know this point is the point 0, 1, so the y value is 1, right? So what angles can I put, or rather, are there any that I cannot put? The answer is you can put in anything, right? I could put in, I could go negative pi over 4, right? And I'd end up at the point root 2 over 2, comma, negative root 2 over 2, and that has an answer, right? Clearly, there's my output. I could put in anything. I could put in 486,000 if I wanted for my angle, whether it's in degrees or radians. So it turns out that the domain here is any angle that we want. So theta from negative infinity to infinity. And hopefully we remember interval notation. Maybe I will do a brief recollection on interval notation. If enough of you watch this video and you write me and say, hey, could you do a video? I will do one. Okay. Now the more interesting question is, what are the possible outputs of this function, right? What are the possible outputs of sine of theta? Okay, we know we can put in any angle that we want, but what are we going to get out? What's our largest y value that we're going to get out? What's our smallest y value that we're going to get out? Well, hopefully looking at the unit circle, we can see that for any point on the unit circle where we could possibly consider evaluating a trig function, the largest y value is going to be way up here at the top. It's going to be the highest one is going to be 1, and the lowest one is going to be all the way down here. This is when the y value would be the smallest, right? It's the most negative. And there's no other choices, right? Like, you can get every number between them, but you cannot get a value of 2. Okay, you cannot get a value of 3 or something, right? The largest and smallest y values here are going to be essentially from -1 to 1 and anything between. So as a reminder, the brackets mean that we get to include the endpoints, right? So we get to include 1 and -1 in our calculations here. And the bracket means up to, but not including. Okay, and the reason why we have to put that for infinity is because technically speaking, infinity is not a number that I can touch and hold in my hand, and so we can be every concrete number up to infinity. Okay, so that's it for sine. That wasn't too bad. How about for cosine? Right? How about for cosine? What would the domain be? Well, the domain is the same as sine, right? We can pick any angle that we want, right? And at any of these angles, I can tell you what the x value is going to be, right? That's cosine. So the domain for cosine is going to be anything that we want, right? Any angle that we want. What's the output? Well, again, very similar, right? The largest x value here is going to be x equals 1, and the smallest x value is going to happen right here when x is equal to -1. So, it's good. Our possible outputs here is going to be from -1 to 1. And now you'll notice that I'm putting y here and y here just because that's what we typically use for our output. If that's confusing, I'll just say that the range is just this set of values, if that makes it a little less confusing, okay? So the possible outputs for our cosine function go from -1 to 1 and any number between. So now let's look at the more interesting case. The more interesting case here is tangent. I'll just go down here so it's nice and neat. So what about tangent of theta? Okay, when we talk about tangent of theta, we talk about the domain and the range. Okay, what could we say about tangent of theta? Well, the important thing here is that tangent of theta is a little bit tricky in that tangent of theta, while it looks nice and innocent, is the same thing as sine of theta over cosine of theta. That was shown in one of the last videos of why that is. I believe it's when I introduced the tangent function. So if you don't remember why this is, please do go back and just watch it. I think I put a timestamp in it as well. So it's super easy to find. But you'll notice, right, that here talking about the domain isn't so easy because while I do agree that individually sine of theta can be anything, okay, on its own, and cosine of theta I can put in anything. I said could be anything, but you can put in anything on its own. But hopefully we recognize from pre-calculus 1 that this is a fraction. And fractions have problems when the denominator is equal to 0. So if the denominator equals 0, we have problems. Okay? And more specifically, we would get, if you also remember from Calc 1, or not Calc 1, pre-Calc 1, we would get asymptotes is what these are called. We would get asymptotes. Okay, really fancy word, asymptotes. So essentially, right, so far, our first guess is that, the domain of tangent could be anything. And then we have to modify that, right? Except for whatever values of theta, whatever theta makes cosine of theta equal to 0, right? Because then we have trouble. So again, here's our unit circle to kind of help us with our thought process. So there we go, right? So there's our unit circle. And so the question is, for what angles, right? The thing that we really need to figure out now is, for what angles, for what theta will cosine of theta equal 0? And remember that this is the same thing as asking, essentially, when is x equals 0? When does x equal 0 on the unit circle? Okay, because cosine is the same thing as the x value on the unit circle. Okay, and while that only happens here, right, it happens up here at the top, and it happens down here at the bottom, right? This is the point 0, -1. This is the point 0, +1. Both those points have an x value of 0, and so this is where we're going to run into problems with our denominator, with cosine of theta equaling 0. Now the question is, what angles are these? Is it just pi over 2 radians and 3 pi over 2? Well, the answer is no, right? Because I could go all the way around, right? I could go to pi over 2, and then I could keep going to 3 pi over 2, and I could keep going some more, and I'd end up at 5 pi over 2, right? If I take this number and I add 2 pi to it, I end up at 5 pi over 2. If I keep going, I'm going to end up at 7 pi over 2. I could go the other way, right? I could have gone down here, and this is the same thing as negative pi over 2, right? And so on and so forth. So in other words, right, so we're going to adjust our domain now to say that that theta, you could roughly say could be anything, right, except maybe I'll make a small list of, maybe -3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, right? And so on and so forth. It continues on in both directions depending on which way you spin, right? Theta could be anything except for those values, okay? And so, one way we could try and shorthand this is we could look at this and say, okay, what is like the difference between all of these, right? Theta can't be pi over 2, but you'll notice that the gap in either direction is just plus pi, right? If I go this way, I'm going to run into trouble. If I subtract pi, I end up here. If I subtract another pi, I end up here. So the idea being that if I add or subtract any multiple of pi to this number, and I'm just picking pi over 2 at random, you could start anywhere. But the idea is that no matter which of these you pick, if I add or subtract pi to it, I'm going to run into an issue, right? I'm going to run into a place where cosine of theta is equal to 0, and it makes our tangent blow up, and life is very sad. So how we're going to fix this, or not really fix, how we could shorthand this, one other way of writing this would be to take all of this, and I'm going to write it in the following fashion. I could say that the domain is any theta that is not equal to pi over 2, or any pi multiple of of that. Actually, yeah, any pi multiple, right? So what does this mean? And what is this k? So where I'm going to say k is what we call an integer. And so an integer here is going to be a number like dot, 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 -3, -2, -1, 0, 1, 2, 3, dot, 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 right? It keeps going, okay? So let's kind of look at what I just shorthand wrote without really much justification, just to make sure that it makes sense. Tangent of theta, I can put in any angle that I want, and I will get some answer, except for if I were to put in pi over 2, because we'd be blowing up there. And if I were to add any multiple, if k is equal to 1, I'd be adding pi, and I would end up at 3 pi over 2. If k is equal to 2, I'd be adding 2 pi, and I'd end up all the way back at 5 pi over 2. If k was equal to 0, this wouldn't exist, and I would just be at pi over 2, which is, again, still a problem, okay? If I were doing k is equal to -1, then I would be subtracting pi, and that would basically take me from pi over 2 all the way down to negative pi over 2. And so this is just a really nice, concise way of writing the domain for tangent of theta. So I have a lot written down, and now I'm going to erase it all to kind of just clear this all up and kind of just tidy all this up. And so how would I write the domain now that we have all of this? Okay, now that we have all this, and hopefully you wrote some of that down in your notes. How would I write the domain? I would say the domain could be any angle that is not equal to pi over 2 plus any multiple of pi, where k is basically just some integer, okay? This is Z, it's German for Zahlen, Zahlen. And it basically is the set of integers, okay? Set of integers. This is much higher level math than we are at right now, but it's a very nice, neat way of writing. You could also just write in English, k is any integer. That would be fine, okay? So now, more interestingly, is what is the possible range, right? What are all the possible y values we could get out, right? What are the possible outputs for this function tangent, right? What are we going to get? Okay, well, let's see here. This is going to kind of be deductive reasoning more than anything. And we know that sine as a function is, sine, the range of sine goes from -1 to 1. And cosine goes from -1 to 1, and we're trying to avoid when it's 0. And so you might be inclined to say, oh, well, the range of tangent is just going to also be from -1 to 1, because how could you get anything else, right? And I'd say that your answer is wrong, because imagine a scenario where sine is equal to, let's say, something close to 1, or maybe sine equals 1, and you're dividing by a value of cosine that's really, 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 really small. Okay, right? Because sine, this is a totally valid value for sine, which means cosine, I could pick anything that I want, right? Because we're trying to cover all of our bases. And a number that is in this set that is not equal to 0, it's close to it, would be like 0.0000001. Well, what could you tell me is the value of this, right? We take a number and divide it by something super duper 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 tiny. Well, again, from pre-calculus 1, this is going to roughly translate to something very large, okay? Very, very large. And the theory being that eventually, if we make the denominator even smaller, this is going to evaluate to positive infinity. And likewise, we can do the same thing, because if I put a negative here, right, if I put a negative here, well, this thing's still going to be very, very large, but now it's going to be a negative infinity, right? You can plug it into your calculator to verify. And I could get any number between it, right? Because if let's just kind of reason this, right? If the denominator, right, if cosine was equal to like 1/2, which is a totally valid value for cosine, then this would equal what? Well, this would equal the number 2, right? 1 divided by 1/2, right? Keep, change, flip. Dividing by a fraction is the same thing as multiplying by its reciprocal, would give us 2. And I could, cosine can also be negative 1/2, and so I'd get negative 2. And so it's looking like, and it turns out, that the range of the tangent function, the possible outputs that we could get, is anything from negative infinity to positive infinity, courtesy of how sine and cosine operate. So when the dust settles and we erase the stuff that's on this board that's a little bit extra, when the dust all settles, and I just try and make this super neat, this is what we have. We have the domain of tangent is any number that we want, any angle, except for pi over 2, or any pi multiple, okay? Any integer multiple of pi. And the output, possible outputs, negative infinity to infinity. If you don't believe me, try some values in your calculator. Try some angles in your calculator to kind of reassure yourself. Okay? So that's for tangent. Let's go ahead and try the other two because we only have 2 left to go. So we have secant of theta, which is more affectionately thought of as 1 over cosine of theta. And then we have cosecant of theta, which again, right, opposites attract. This goes with 1 over sine of theta. All right, so let's talk about this. Well, the nice thing is we literally just did this because secant of theta is 1 over cosine theta. We just answered the question. Right, when is this going to have problems? It's going to have problems when the denominator is equal to 0, aka when cosine of theta equals 0, but we know that. We said cosine of theta is equal to 0 at pi over 2 and any integer multiple of pi, right? So where k is an integer. And what are the possible output values? Well, we did that too, right? Well, kind of. Right? Can we get anything? Let's see. If I put in a really tiny number, like if I take this and I put in 0.01, this is going to equal 100. If I put in negative 0.01, this is going to be negative 100. Let's see. So I can definitely get big numbers and very negative numbers. Let's see. What happens? Cosine. Let's see. That's if I put in small numbers. What happens if I put in a positive 1 here? I'll get 1. Put in a negative 1, I get negative 1. Okay, so that's fine. So what can't I get? Well, can I get a fraction? Right? Could secant of theta equal 1/2? Right? Can it equal 1/2? Well, in order for it to equal 1/2, cosine of theta would have to equal 2. Which we know is not possible, right? Because cosine of theta, this cannot happen because cosine of theta is trapped between -1 and 1, right? So we can't do that. And it turns out that we literally cannot get any fraction, right? We cannot, the only numbers that we can't get is any fraction because it would require cosine of theta to be equal to 2 or 3 or 3.5 or 4 or 100 or whatever, which cosine can't be any of those values. So it turns out that the range of secant is any number from negative infinity to -1, including, right, because cosine can equal -1, so that's fine. And then we have to jump over the middle section and restart on the other side, like so. Okay, and again, I encourage you to just plug in some values of your own to kind of verify this. Just copying this down will not help you. Okay, you are not going to learn anything from just copying this down and be like, oh yeah, I've learned it, right? If that was the case, I would have learned to drive stick by just reading a book and writing some stuff down, right? That would have been great. Okay, you got to actually do it. So how about cosecant? This would be a good exercise for you to pause the video and try it on your own before I do it. Okay, because we're going to take the same approach and say, okay, well, here, where do we have problems? We have problems in the denominator when the denominator equals 0. So sine of theta equals 0 is a problem. And again, this time I'm not going to bust out the unit circle. We're just going to use our intuition that, that this happens. When is the y value on the unit circle equal to 0? Well, it happens at 0 degrees, pi, 2 pi radians, right? 3 pi radians, ... And it also happens at negative pi, right? Negative 2 pi, ... It happens for a lot of values of theta, okay? And so a way we could try and shorthand this would be to say, all right, well, if theta is equal to, you can pick any of these values. If theta is equal to, let's pick pi. No, you don't. Actually, well, let's pick 0. 0 is a nice one. So if theta equals 0, we have trouble. And again, if we add any integer multiple of pi, right? If we go pi this way, we go another pi that way, we go another pi this way, or we subtract any multiple of pi, right? So for k in the set of integers, this is going to give us a problem. So we cannot have theta be equal to any of these angles. And because 0 plus something is just the thing, I'm actually just going to go ahead and erase this. Scooch this all a little bit closer, like so. And there we go. There is the domain of cosecant of theta, right? Here's the domain of cosecant of theta, right? It's any value of theta that we want, so long as we don't pick 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, so on and so forth. What do we think that the range is going to be? Well, last time I checked, the range of cosine goes from -1 to 1, and the range of sine goes from -1 to 1. So using the same logic that we just used previously for secant, the range of cosecant should be the exact same thing, because sine and cosine of the same exact set of outputs. So why would it be any different? All right. So we have this. Now, why have we done this? Why have we taken the time to talk about this? Because it's going to be very interesting for us in solving problems later, where when we have the machine of a function and we're saying, I would like you to solve something that involves this. It's a good idea to know what things can go inside, right? What things are allowed to go inside and what things are not allowed to go inside. So we say the input, we can put anything except for secant. It's pi over 2 plus k pi, where k is an integer. And what are we going to get out? Well, we're going to get out any number from -infinity to -1, inclusive. And we could get out anything from 1 to infinity. We can't get out fractions because, again, secant is 1 over cosine of theta, and cosine of theta could never be a whole number larger than 1, or any number larger than 1, I should say. And vice versa in the negative direction. It can't be -2, can't be -3, -4, etc. Okay, so that's why it's kind of interesting to us. We're going to get into this obviously a little bit more in the coming weeks, but for now, this is just something to keep in our head, that these trig functions are actually functions. They have domains, they have ranges. I will say that the ones I'm going to focus on the most in this class are sine and cosine, because they are the bread and butter of essentially figuring out the ones for tangent and secant and cosecant and so on and so forth. And as long as you have a really good understanding of how those work, then you will have a good understanding of pretty much everything that we're going to do in this class. So I would spend your time focusing on those, understanding why they work the way they work. And then in the next video, we'll be kind of jumping into, which is going to be for week 3, we're going to talk about, just like you would with any function, how do you graph